might get into it straight away if I'm happy with that. So I'm going to be talking about qualitative modelling and network modelling. Now, just before I start, again, I always ask this just to see who's done what already. Who's used qualitative modelling? Come on. And who's done any social network analysis? Good, great. So there's not many. So I've pitched it. Hopefully you'll be able to follow what I'm going to be talking about. And I'm sort of giving you a taster so that you know what the modelling tool is about and that you can apply it if you want to later on. So again, come talk to me afterwards if you are intending to use it. So qualitative modelling, and just following on from the basic stuff, qualitative modelling, you only need to know whether a relationship is present or absent, positive or negative. So you don't need to have any more information about the data than that, which is nuts. So jumping straight into it. So I thought I'd start with an equation. So qualitative modelling, before it could be developed, it had to wait until Lotka and Volterra did their, developed their mathematical relationship with predator and prey. So here you can see that key relationship that most of you being sort of natural scientists in the room know about. The predator and prey relationship, if you can see this down here, the predator benefits from reducing the number of prey, the food, and the prey increases the benefit to the predator. So the qualitative models are all based on predator-prey relationship, and Richard Levins is the person who developed qualitative models. So he started off with the mathematical relationship between predator and prey, and he developed what we call a community matrix. Now, most of you have got some maths background. The community matrix, any diagonal, is basically the self-effect. So this one here shows that there's a negative impact of the predator on the prey. On this one here, there's a positive impact on the prey on the predator. Simple. And again, this is the sign diagram, what they call, that I already explained. Got it stacked. Yeah. My back? Yes. Good. I'll try and go between that side and that side so you guys don't get a sore neck. Okay, so I think that's about it for the maths. So just a little bit more about the sign diagrams. This is the predator-prey relationship that I talked about before. It doesn't have to be predator-prey, so you can also have competition, right? So animal 1 reduces the number in animal 2, and animal 2 also reduces the number in animal 1. So that's like these two, these things from, it was, I can't remember, it was an island, but basically they compete for space. Amenalism is where, so for instance with bacteria and penicillin, the penicillin has a negative effect on the bacteria, but the penicillin doesn't have, there's no commensurate relationship there. Mutualism with the clownfish here, basically they both have a positive effect on each other, and commensalism, this bird has a positive benefit from the cow, but the cow doesn't. So these are all the different relationships you can have in the natural world. Oh, sorry, I'm going the wrong way. Yeah. Okay, so coming back to the community matrix. So if you look at this notation here, we have small fish, we have large fish, and we have a fishery. So there's positive and negative relationships between all three of these, which you can show in the community matrix by the change in small, there's a negative effect of small fish on small fish due to an interaction with large fish. So the large fish basically is the small fish, right? And here you can see that there's a self-effect, which is basically what was shown yesterday in the graph where you get a tank full of fish. If there's too many fish fish are going to get crowded, so there's a negative self-effect. You only have so many fish. So that's on the diagonal here. So you don't need to have all those numbers in there. Basically, this is showing the same thing. You have a positive, a negative, or an absence. There's no interaction between the small fish and the fishery. So basically, this means that the fish isn't being caught by the fishery. So what can they tell you? So if you build a qualitative model, you're basically using the key drivers to predict change. And as I said, all you need to know is whether that interaction is positive or negative, absent or present. You can assess model stability, and you can use it to identify gaps in the information. So the question before about using whether Bayesian models can test the accuracy of the science, these models are really, really good at testing whether people have a different opinion about the way the world works. So, and I'll show you that hopefully as I go along. And they're really, really easy to produce. So if you think about a model, usually what you do first before you build a model is to build a conceptual model, right? You have all your variables and you figure out the relationships between your variables. That's a conceptual model. Well, this in a way is one step up from a conceptual model because you have whether it's positive or negative. So they're easy to build with stakeholders. So I'll give you an example from South Africa. Kelly, you correct me if I'm getting anything wrong. So the Benguela ecosystem is off South Africa. Basically in that ecosystem there's hake, and the hake gets eaten by seals, and there's a fishery. So the fishery catches the hake, so there's a negative effect on hake. The seals also have a negative effect on hake. Very simple. Now, there was a shortage of hake, so what people thought was we'll go and cull some seals. Because if you reduce the number of seals, that should have a positive effect on hake, which will have a positive effect on the fishery. Right? Logical. However, as it turns out, there's two species of hake. So there's species that live in the shallow waters, that's the capensis. So you have juveniles, and you have adults, and then there's species that live in the deep water. So there's adults that live in the deep water, and juveniles live in the shallow water. As it happens, the adult capensis predates on the juveniles from the paradoxes. So the simple model here is actually a little bit more complex. There's a delay in it, that's why it keeps speaking.
Maybe we should all switch off the internet. That help?
Now it's stuck. Stay there. Yes, okay. So here we have the simple model, and here we have a bit more complicated model. So again, the seals, the adults, and the fishery are still the same. Here we now have the juveniles of the shallow water species, so they have two positive areas between them because you have more adults, you get more babies, you get more adults, right? Simple. Now, we have this relationship in there where this shallow water species predates the juveniles of the deep water species, the adults of the deep water species, and also the fishery. So the fishery is both on the adults of the shallow and the adults of the deep water species. So what actually happens if you kill seals is that you reduce the predation on this one here, which has a positive effect on the fishery. But because you increase those ones, you decrease the predation of the juveniles, which decreases the adults in the deep water. And in fact, the biggest part of the fishery is the adults from the deep water. So in fact, if you kill these seals to increase the fishery, to get more fish out of the sea, what you're doing is in fact decreasing the fishery because you're relying on these adults from the deep water. So by building this simple qualitative model, you can see that, and you can do this just by putting a group of scientists together, you can see that if you think through your strategies, you might have an unintended consequence of trying to do some good management. So that's the first example. So I've got also an example from Australia in the banana prawn industry. So the banana prawn industry had a similar problem. There was fewer banana prawns, and they wanted to figure out what to do about this, because there was all sorts of theories about what might be happening in the banana prawn industry. So there was a theory that there was overfishing. There was a theory that there was a change in the environment which was causing the banana prawns to disappear. There was a theory about pollution. There was a theory about fishing effort. There was different theories, and so what people did, well, they said, well, we can't figure out what's going on with these banana prawns. We'll get a group of scientists in the room and build a qualitative model and to try and figure out what's happening. So, first of all, they started with the banana prawn life cycle. So you have adults, larvae, juveniles, maturing adults, and that's how it works, right? You get more adults, more larvae, more juveniles, more maturing adults. That's the relationship between those species. So this is basically the basics of the model. Again, you have prawn food, nutrients, you have prawns, and you have predators. Is everyone still following? Yeah. So, to start the model, we'll start with the life cycle. We have prawn adults, prawn larvae, prawn juveniles, and prawn maturing adults. So they live in different parts of the ecosystem. These guys live offshore, the adults and the larvae. Then they come inshore, the juveniles come inshore into the estuary, and and then the maturing adults live inshore. So we have I'm not the technologist, it's not working. Sorry. My apologies. I'll stand on this side for a minute. Maybe that's better. So we have the centre here, which is the life cycle. We have the predators, which have a negative effect on each of the life stages. We have the food, the nutrients, and we have some competition for these nutrients, which is the CO, in the different parts of the ecosystem. Now, that's the biological system. We can put in the human system. So another really neat thing about qualitative modelling is that you can use different parts of the system to represent them. So we have recreational fishes here. As it happens, the recreational fishes don't go for the prawns, but they fish the predators of the prawns. So the recreational fishes have a negative interaction with these because they take these out of the system and these ones. Now we have commercial fishes who fish this predator as well, and they fish the adult prawns. And so the other thing we can do then is represent some of the interactions in the human system. Now this is a very simple one. If the prawn catch goes up, we have a higher value of this, the price will go down. Now again, this is a very simple relationship, but it's one that generally holds. If the price goes down, the effort goes down, because it's a negative and a positive, and so the commercial catch will go down. So that's an interaction there, it's a feedback system. So we have the human system in there, we have the biological system in there, and we can also have the environment in there, and the habitat. So here we have turbidity. So turbidity has a negative effect on this predator and on this predator. So we have, I'll go with this one anyhow. So we have the mangrove habitat. It has a negative effect on this predator. We have early rain, which has a positive effect on the different parts of the life cycle, also on this predator. We have offshore turbidity, late rainfall, and salinity. So late rainfall has a negative effect on salinity, which has a negative effect on prawn adults. So basically, you can build up this qualitative model very easily with a group of scientists in the room. Most people will know whether it's a positive or a negative effect of absence or presence. The most difficult thing about building these is to not make it too complicated, to not get too many of these variables represented. So what you can do then, so that's all well and good, you can build this model and it'll give you an insight into how the system works. And people might have a different opinion about this, so that's also a really powerful thing. While you're building it, some of the scientists might say, no, well that's not an interaction that I think is correct, or that doesn't work like that. So you can build 2 or 3 of these representing different realities in a way. So that also brings out some of these disagreements in the science. Or you might have a group of fishermen and scientists in the room giving each other information about what's happening out in the ecosystem. Again, that brings out disagreements about the way things are happening. So then what you can do is you can perturb the model. You can say, okay, say we have a really early rainfall event. So we're going to push the model by saying, okay, we have an early rainfall event. What might happen? So an early rainfall event has a positive effect on the yellow nodes that are coloured yellow because of these, the signs of these arrows and the community matrix that sits behind that. It has a negative effect on the blue ones. So an early rainfall event, ironically, has a negative effect on these recreational fishes because of the interaction between early rain, turbidity, and this particular predator. So that's something you can take away from the model, right? So obviously early rainfall is really good for the prawns, is really good for the industry. Price will go down, effort will go down, and there's a feedback system there. So then there's the ones that can't be resolved in these models because it's plus and minus, and you have these feedback systems. Sometimes there's a plus coming in and a minus coming in, and you don't know what might happen. So it can also tell you, okay, we've got all these relationships, but we don't actually know what's going to happen here. So, which is also really powerful. And then there's one where there's no effect. So an early rainfall event has no effect on these nutrients and these predators. So that's the sort of thing that qualitative models can do. There's a lot more. In fact, if you have a model like this, you can run it for these. You can get probabilities of a positive or a negative effect for some of these variables. And if you run the model over and over and over again, a bit like Markov, you can get probability distributions, which you can then chuck into a Bayesian model and run a Bayesian model with that. So, and again, where you have a 0 or a so these are obviously the probability of a positive effect, probability of a negative effect, and the ones that are 50-50. So these qualitative models can lead you on to a Bayesian model, which can be very nice as well. So just summing up, this is all I'm going to talk about, qualitative models, but so basically just summing up, there's very few data required. You only need the signs and the interactions, and you can get a positive effect, a negative effect, or a reciprocal effect. You can put in things like a negative effect of female education on birth rates. It doesn't need to be animals. You can put the animals with the people and the environment. You can get any type of interaction, as I said. Well, that's actually what I just said. You can get increase in wealth, increase in female education, reducing birth rate. It's a well-established relationship. You can investigate indirect interaction, so an increase in small fish, what is the impact on the fish feed through the lunch, so you can get direct interaction and indirect interactions. And as I said at the start, they're really good for producing with stakeholders because they're so intuitive, everyone can do it. It's not difficult at all. That's the end of qualitative models, and I'll go straight on to social network analysis unless anyone's got any questions at this stage.
So this was great.
I'll give you the mic.
Thanks. I think this is really interesting. One thing that struck me in your banana prawn example was that you don't have the self-feedbacks, and I'm just curious, it seems like those really come into play when you're approaching carrying capacity, but they were in your sort of preliminary examples. I'm just wondering if there are ways of making things like that conditional, or if you find in most of your practical experiences that those are details that just don't come out when people are thinking about the status of the way they perceive things at the current time.
Thanks, Kathy. The reason I went to them was basically because the diagram gets really sort of crowded, so I left them out for that reason. But your question is entirely valid. Usually people don't think about it, and usually what happens is you build the model, and then the scientist who is doing the interpretation of the model and the maths, etc., will put the self-effects in where appropriate. Yeah. So usually people, well, if you put them in the workshop and explain what's happening, people will accept it. But usually it's something that you do afterwards. Does that answer your question?
Yeah, I guess so. And so then the scientists might only put them in for populations that they know are sort of where there is some potential resource limitation coming into play.
Yeah. And that applies both in the natural and the economic system and all parts of the system where it's self-limiting, it could be self-effective. Yeah. Or it can be positive, although there's not many instances where it's positive, I think. Yeah. So another...
Finish.
I am finished.
You are finished, okay. Yeah, this is more a comment. I like the way you made a connection from qualitative to basic, right? And this is, I'm going to say something that you can say it's all nonsense. So, it seems to me that if you want to do quantitative modeling, the prerequisite is qualitative modeling. You have to set up your hypothesis. You have to check out your theory. Yes. Yeah, sometimes I feel like it's going to enter my mouth. Oh, gosh. So it seems to me that to do quantitative analysis, you need to do a good qualitative analysis. Otherwise, your models will just be, you have to set up the hypothesis. So, okay, that's the first one. And then there are situations where you cannot do quantitative analysis, and therefore, qualitative analysis will then stand on its own legs, because that's all that you can do. Does that make sense, or is it?
Yeah, no, that makes absolute sense, and I think that the power of these ones is that it makes you think through the logic. So if I would do a quantitative model, I would always do a conceptual or a qualitative model before, because you need to know the relationships that you're showing in your quantitative model. And they're intuitive, right? They're not... Yeah. Do you want to say something? I can see you sort of...
The best part about this is that both through qualitative cluster analysis, but also the Bayesian part, you can actually test the hypothesis. You can say, if this hypothesis is true, we'd expect this distribution of data points. And if you're not seeing that, you know your model's wrong. You can also know you've got structural uncertainty right from the start. So for me, this is fundamentally the first step that every modeler should use for every model. Because it characterises so much uncertainty about what's happening, it helps you think through options really quickly, and because you can talk to anybody to do it. So this is what I was talking about yesterday with drawing in the sand with people on islands who are completely illiterate. Anybody can get this kind of information straight away. And I guess the other thing about qualitative modelling that I find really powerful is that it makes really clear that there's different perspectives of how the world works, especially if you're in a room full of stakeholders who have really different political views. So if you're doing it about, say, a non-science, like an economic or social issue, it actually becomes really apparent that people think the world works really differently. And that's valid. I mean, the world works differently for different people. So that's really nice, because people in the room will realise that not everyone thinks like them. And that's always a nice thing. Let's go and take a sip of water. So the nice thing about going from qualitative modelling to network modelling is that it also involves nodes and edges, as they call them. So the notation's quite similar in a way. Again, I'm going to jump straight into it. I've got some introductory slides just about networks, and then I'll just tell you a little bit about the history of networks, which I find really fun, but you find as well. So there's all sorts of networks. There's physical networks, so a river is a network. The blood system in the is a network. The internet, roads, everything around us is a network. So there's physical networks, and then there's interaction networks. So gene protein networks, airlines networks, here, paper citations, trade flows, everything can be represented by a node, a line, and another node, a connection between 2 points. And then we have social interaction networks, and I'll be sort of focusing on the social network analysis. But basically, social network analysis is the analogue of food webs, right? Food webs is the connections between animals and how the ecosystem works. Social interaction networks is basically the way people are connected and how that works. So they're very similar, and all the statistics that I'll be talking about can be applied to both. The reason I'm talking about social ones is because the social network analysis have been really good at figuring out the relevance of positioning network and the relevance of the connections. So it's easier to explain it through social network analysis. Okay, so this is just an example of social interaction networks. This was a study done in Hawaii that looked at 967 climate change professionals and the connections between them. They are coloured according to nationality, and one of the things obviously that the study showed was that people connect very well with their own cultural affiliates, but not so well with people internationally. And if there is an international connection, it's usually through one key person in that particular country. And that person is then connected to other people. So they cluster with people. That's a sort of, as you would expect, but it's a nice way. So how did this interest, so there's been this incredible increase in social network analysis papers over the last, say, 10, 15 years. And so where did it actually start? And it starts with this really, I think, small study that a guy called Stanley Milgram did. He was at Yale University. He's a social psychologist. This is the man here, this sort of interesting man. So basically, have you all heard of 6 degrees of separation? Who hasn't heard of that term? Most? No? So, okay, so hopefully I'll show you what 6 degrees of separation means. So I guess in the English-speaking countries, 6 degrees of separation is a term that most people would know. I don't know whether there's a translation that I should have known about. So the research was groundbreaking and basically started the social network analysis. And the experiment he did to establish it is called the Small World Experiment. So Stanley Milgram, how did he get to this 6 degrees of separation? So what he did in his experiment is he basically had an information packet that he sent to some random person in the community. So he sent an envelope. Basically in the packet it had some basic information about a person in Boston who was a stockbroker. And he basically, the person that got the envelope in the mail was asked to send this to the stockbroker if they knew who they were. If they didn't know who the Boston stockbroker was, they were asked to send it to someone who they thought might know that stockbroker, right? So, and if the next person didn't know the stockbroker, they would be sending it to the person that they thought might know the stockbroker, who they actually were on a first name basis with, right? So they had to know them. That science relative knowledge-wise, I think. Okay, so the recipient was then directed to sign his name on a roster, and if the recipient knew the stockbroker, obviously the chain would end. If they didn't know it, they'd put their name down and send it to the next person. And then the package eventually would reach the Boston stockbroker. So this is what those chains look like. This one from a widowed clerk to a self-employed friend to a publisher to a tanner, anyhow. So he got to the target person after the 7th. This one got to the target person after the 3rd. So basically, there were 20% of the parcels that actually reached the target stockbroker, average chain length, the average number of persons in the chain was 6.5. So this is where the term 6 degrees of separation comes from. So basically, there was a movie that was made about this. And this is a line from the movie, and I'll just read it out. It says, everybody on this planet is separated by only 6 people, other people. 6 degrees of separation between us and everyone else on the planet. And the President of the United States, the gondolier in Venice, it's not just big names, it's anyone. A native in a rainforest in Tierra del Fuego, an Eskimo, I'm bound to everyone on this planet by a trail of 6 people. So this is where social network analysis started, and the movie with Will, that basically, sorry? They basically made this quite famous, and in any English-speaking country, most people would know that this concept of 6 degrees of separation. So why does this 6 degrees of separation exist? Why is there such a small world? Why is everyone connected to everyone by only 6 degrees? So we think about going back to the notation that I started with, the nodes and the edges, the connections. Here we have 12 people, or n is 12. We have no connections, so the probability of being connected is 0. And then we have what we call an average degree. So K is the number of links, so these links are these black lines, and the average degree is the number of, the probability of a person being connected, of P divided by N basically, or times N. So P, K, and 0 here, in this network here, everyone's connected to everyone. So we have, again, N is 12, the probability of being connected is 1, K approaches N, so basically in this case, K is 12. Does that make sense? Because this is key for the next couple of slides. So, I wish this would work because it steps it through. Okay. So in this network here, each person is connected to 2 neighbours on each side, so this one and this one. And it takes 3 steps to get from A to B. Sorry. So it goes 1, 2, 3. Yeah?
Ingrid, just press it on the computer instead of the phone.
Then I have to go and stand over there. That's the only thing. Yeah? I'll keep trying. Is it really annoying, is it? I'm sorry. No? Okay, so it takes 3 steps to get from A to B. 1, 2, 3. Now, put in a few random nodes, right? Now put in these random lines. Draw them from anywhere. So these couple of random lines basically reduce the number of steps from A to B to 2. So you can now get to number from here to here to 2 steps. So these are just a couple of random lines in this organized network. So I've reduced the number of steps to get from A to B. So you can say something interesting when, for different values of P and K, so the probability of being connected and the number of links, or the average degree, as N approaches infinity. So we've got, again, some different networks up the top here. This one, as we know, N was 12, there was no probabilities of being connected, and the average degree was 0. We've got N is 12 for all of this, obviously. We put in a couple of lines, and the probability of being connected here is 4.5%. Here it increases to 9, and here the probability of being connected is 1. So here K is N, here K is 1.08, and K is 0.45. So this is your average degree between these different networks. Now, a key to these networks is what is the size of the largest component in the network. So the size of the largest component is 1 here because no one's connected. And this one is 5. It's 1, 2, 3, 4, 5. Right? There's 5 nodes that are being connected here. So that's the size of the largest component. For this one, the largest component is 11. There's only 1 node that's not connected. So what is the diameter of the largest component, 0 here. Here it's 4. 1, 2, 3, 4. In this one it's 9. 7. 1, 2, 3, 4, 5, 6, 7. I lost count there. And in this one it's 1. And what's the average path length? Basically, again, the average path length is 0, and this one's 1. So you get my sort of drift here, right? You can just do some counting between the networks and the connections, and you get these little bits of information. So what I'm trying to get to is, what does this mean in terms of a small world? Why does a small world exist? And that becomes obvious here, hopefully. So here we have those 4 networks again. We have our k values here. So k was smaller than 1 for these first 2. It was 0.54 here. In this one it was 1.08. So at k is 1, we have a component that's where the 11 nodes were connected, and this one where k is larger than 1. So if we plot that on this graph here, you can see there's a phase transition here. So what's happening is that the percentage of nodes connected between the different networks, if you go at a degree greater than 1, here is the peak. Where k equals 1, we have a giant component, 11. The diameter of the network peaks at 7, and the path length is 4.5. So at 1, there's a peak diameter of 7, after which it shrinks to 1 again. So it comes down again. So at this point here, we have a phase transition. And it basically means that, because everyone usually knows at least one other person, so everyone in the room would know more than one person. So the chance of being linked to many people through knowing one other person is really big. So we're basically saying is that this explains why we live in a small world, why there's only 6 degrees of separation in this world, because we all know at least one other person. So you are basically very easily connected to at least 6 removed from one other person. So this is why a small world exists. So going from the small world example now to the structure of these networks. So I'm actually going away from social networks a little bit and coming to an electricity grid network here. So this is what they call a true grid. So basically it's normally distributed. So here we have a bell curve of the number of links. In this one here, this centre here obviously has a lot more connections than some of the other ones, which means that it's got a power law distribution. So there's a few hubs with lots and lots of links, and there's a lot of hubs with not many links. So if you take out, so if there was some attack and this power grid station could be taken out, then the whole of America would be out of power, right? Whereas if you take the same one out in this particular example, all the other ones would probably still keep going. So having a power law distribution of links means that you have a very sensitive network. You can, so if you have an information network or a social network and there's one key person in that network and they stop to be part of the network, then the whole network falls apart if you have a power law distribution. Whereas if you have a normal distribution, then one person less doesn't really matter so much. So many networks in the real world are degree law distributions or power law distributions. So if you think of an economic system, about 20% of the people own about 80% of the wealth. If you think about friendship networks, usually it's about 20% of the people that have 80% of the connections. And basically in the real world, it's the Pareto distribution, 20% of wealth is spent. So basically that distribution is something that appears in the economic world all the time. So why would ecologists want to know about social network analysis? So these shapes of these networks, these power law distributions and these normal distributions, can tell us something about the structure of the network and the topology of the network. So it depends how the network is shaped. so whether it's a power or not, and also where that person is in the network. You can make some assumptions about what the role of that person is depending on where they are in the network. So, and I'll just have some slides about the statistics now. If you think about a social network, you can have a network, say a friendship. So point A is a friend with person B, which means that if I'm a friend of yours, then yours is a friend of mine, right? So it's an undirected network. Whereas here we have a directed network. So it could be, for instance, be a financial transaction. So there's a financial transaction going from A to B, but B doesn't, and B has a financial transaction back to A. But there's a financial transaction from C to B, but there's no transaction back. So a network can either be undirected or directed. So the matrix that underlies that is different depending on whether it's a directed or an undirected network. So two things that are important in these networks that tell us something about the way they work and the importance of the people in the network. The first is connectivity and the second is centrality. So connectivity refers to how someone in one part of the network is connected to another part of the network, and centrality is about location, so where in the network you're located. So talking about connectivity first, it's about the path between one actor and another. So if we start at actor A here, it's the distance from A to B. So there's one step from A to these nodes, there's another step to the next 5 nodes, and there's another step to these ones, and then there's another step to these ones, and one last to the other one. So the number of steps that you are removed from another person is important in the social network. So centrality is all about location. So that was connectivity. So it's basically just measuring the steps in the network. Centrality is about where you are in the network, and it's important in terms of the cohesiveness of the network, as I showed with the power relations or the power stations. If the key power station falls out, then that's really important. And there's 3 statistics that you can compute to do with centrality. It's degree centrality, closeness, and betweenness centrality. So the first one, degree centrality, is it's the easiest one to think about. So this one here has 7 connections. This one here has 3 connections. This one here has 2 connections. And in this network, everyone has 2 connections. And in this one, in the linear network, the middle ones have 2 connections and the other one is 1. So degree centrality can be really deceiving, because if you look at this one here, you think that this one is the central one, but in fact it's these ones. These ones have 5 connections and this one's only 3. But intuitively you'd say that this person is really important in this network, right? Which is it's the key person, in fact, that stops interaction with the others. And that's sort of measured by closeness centrality. So this closeness centrality means that this person controls the information going through the network, so it takes only one step to get to all the others, whereas in this one here, the highest value is observed for the middle one, because they basically control the spread to all the other nodes if something gets propagated through the network. And you can think of a disease or something that if there was a disease spreading in this part of the network, and that person was immune to the disease, it wouldn't spread through the rest of the network. So the closeness centrality is an important measure. And then there's the betweenness centrality, and this is also, it depends on where the person sits in the path, and it counts the number of shortest paths between different actors. So in this one, it's probably easiest here. Again, it's got the highest value for the middle node there because they're key, because they have the most control. So if you put these things together, if you think about betweenness centrality, again, it's also a deceptive one. If you look at a network, you think that this this person here is the one that controls the network, because everything, if that person fell out, then it would be a really important person. But if you look at the values for this network, it actually turns out that these guys over here are much more important in terms of controlling the flow through the network, because their betweenness centrality is much higher. And the last slide I want to show you is that, so generally we have the centralities, the degree centrality, closeness centrality, and betweenness centrality. If you plot them against each other, if you have low closeness centrality with high degree centrality, you can say that someone has a lot of connections, but is embedded in a cluster that's far from the rest of the network. So if that is the case, then if they drop out, it doesn't really matter for the rest of the network, because they're part of the cluster that's far from the rest of it. You have low betweenness with high degree centrality, so then the player has a high number of connections that are redundant, and the communication basically passes by them. And that's sort of the relationship between the different centralities. So I think I'll leave it at that with this summarising statement. Basically, the social network analysis has a lot of sort of structural concepts that are useful for natural scientists, and that you can figure out things like regime shifts and the structure and the quantities of the flow in the marine sort of system, for instance, in the food web. And there's a lot of applications in biology and ecology that you can apply social network analysis